So here we have our CPU. Here we have we have here a program to execute. But the first thing you must realize is that we can't know where the program is because it's stored in the memory just the rest of the data will be stored. So our program could start here, for example, or here or here. We don't know, and we can know because there is anything in the memory that tell us that the program starts in somewhere. We must know it before executing the program. So, for example, this data here could be an instruction or could be something to operate with. We don't know. So we must tell the CPU where to start executing something, and this is done with the program counter. In this case, our program starts here, but because I know it, I uploaded the program, and I know the program was loaded here, so my program will start in this address, in address tree. Another so once we know it, we can't we need to know which instruction is each data. So here, okay, I'm going to hide it. Each instruction usually has a number to tell the CPU what instruction is. So, for example, in this case, we have the program here. So this information will be interpreted as the first 3 bits will be the instruction to execute, and the rest will be operators for this instruction. So, for example, in this case, is 000. It corresponds to LR1, so it will be a LR1 instruction, and the rest will be the data. Remember that LR1 loads a memory into R1, so it will load the memory positions 0001 to R1, and the same with the rest of the contents of the memory. This will be interpreted as LR2. This will add JO, jump before overflow, and so on and so forth. So then remember we have three here. I'm going to write it. We have a 3. This is the program counter, and we start the execution of the program. So the first phase will be to fetch the instruction. Okay, we need to go to the memory. So through the memory bus, we send the instructions to the memory and get this instruction and load it into the CPU, so the CPU can know what to do. So we put the instruction here. Okay, this is the instruction, and once we have here the instruction, the CPU can decode it and start executing it. So it loads the instruction. Okay, this is an LR1. We have here the memory position we need to load. So the next step will be to go to the memory and go to position 1 and load this into R1. So in this case, we will copy that and load this into R1. And the instruction has finished. And then we need to increase the program counter because this instruction is already executed, and start this cycle again. The processor will fetch the instruction the instruction stored in the memory address specified by the program counter. In this case, the fourth position here. It will move it to the processor. Decode the code information. In this case, is an LR2 of position 0, which we have done here. But the processor must do the same. So it gets this value and stores it in R2. Okay, increase the program counter, and we keep running the program. get the instruction 5. Here, the instruction in position 5. This is an ADD operation. In this case, this part, it has no, it doesn't need an additional information because ADD, we have said that it always adds R1 and R2. And this part, this is an oversimplified CPU. So we have divided our instruction set. So each word is divided into 3 bits specifying the instruction and the next 5 bits of the specifying the operands needed for that instruction. But in modern processors, it's much it's very complex. So for example, for some instruction, you will need to read operators from the next memory position. So it's not always this way. Okay, it depends on the computer architecture. But in this case, we have here an ADD operation, and we don't need this part. So we add these two numbers and store the two numbers in R1. So it will change to 11111000. Okay, and this is a text, but okay, let me put this here. Okay, so this instruction, the ADD, has been executed. So we increase the program counter and again go to the memory, fetch the next instruction. In this case, this one, the jump if overflow. And in this case, we don't have an overflow because the previous operator, the ADD, we have here the results and we don't have an overflow. So it won't do anything. It doesn't have an overflow, it won't jump. So next instruction 7, go to the memory, read the next instruction. Can you see that we are accessing the memory a lot? This is the von Neumann's bottleneck. Decode the instruction STU0, so it will store the content of R0 in memory. So it will store this. This will remove to 0 because 0 here is the operand for this instruction. So we will have here this, and we keep executing the program. 8. Sorry. We fetch the instruction. Okay, fetch the instruction. We have the instruction here. We decode the instruction. This is an STO in position 1 in this case. So we have R1 to position 1. Increase the program counter. Read fetch the instruction. Okay, and this instruction is a halt. So the processor stop. In a computer, you won't be running an alt operation because you have always something running here. We will see it in the next unit when we talk about operating system. But more or less, this is the process of how a CPU in a very simplified way. This is how a CPU works, how the instructions are fed and decoded from memory, and how it runs the operation and executes our programs.